we are going to travel to Nevada, University of Nevada at Reno. We have two presentations from UNR, both presented by Dr. Mohamed MOUSTAFA. The first one deals with robust methods for UHPC early strain determination and quality control for ABC. Dr. MOUSTAFA?
Thank you, Dr. Mohamed. Can you see my screen and hear me well?
Yes, both are perfect. Thank you.
Okay, perfect. So thanks for the introduction. Today I'll be happy to share with you, our progress in two ongoing projects, here at UNR. The first is in the robust methods for UHPC early strengths determination and quality control for accelerated bridge construction purposes. So I have Mohammed Shakir Ibrahim is my student, working on this project. We have, three industry partners, sensors actually, partners, leading partners in or leading sensor manufacturers, from different actually areas around the world, like Lumicon from Canada, Meteorex, I think from Europe, and Geotech, also Northern America. So we acknowledge, their support and help through this process, of course. So why UHPC? UHPC now is becoming very popular, specifically for ABC solutions and connections. And a question that starts, rising in the ABC world, if we want to move on to the next construction phase and we're using ABC UHPC in the connection, in deck field joints, for example, or seismic connection, when are we ready to move on to the next phase? So in Caltrans, for example, you looked at a 12 KSI in 12 hours to see, they have the 14 KSI as the threshold for the opening the bridge for the next phase. So when are we going to reach this 14 KSI? And when some, again, manufacturers sell their UHPC as it's a mix that can reach 12 KSI in 12 hours, how do we guarantee this on site, especially in remote sites when you don't really have a lot of testing capabilities? So the goals and objective of this project is to, check two of the current methods that people have been using for conventional concrete and see if we can use them for quality control purposes and to know, to assess the strengths of UHPC on site, for early strengths characterization, specifically early strengths. That's our focus here. The first is to use cubes instead of cylinders, because cubes, you can test them on the clean sides without the need to prepare the surface or grind as we do for cylinders. Then it might be easier to test on site with minimal preparation. And the second is to, develop maturity curves or use the maturity method in general for informing the strengths of UHPC. And none of these have been, extensively done for UHPC yet. So of course, people have used maturity for UHPC, but no one sat down, to carefully assess if the current procedure, according to the ASTM, for example, does it work for UHPC or not? If it works, what are the shortcomings or are there areas of improvement? So that's what we are doing in this project here. So we did a very, experimental, comprehensive program, which you'll see, later, to combine these two methods together. So when we do the maturity, we put our sensors in both cylinders and cubes, and in the meantime, we compare cylinders and cubes to see if we can have some conclusions on both methods. So let me start by, for those who are not familiar with the maturity method, what do we do for the maturity method? So in the lab, before you start a project, that's what the ASTM, C1074 maturity method, specification would tell you to do. You just, prepare your cylinders, UHPC in this case, and have them in a lab cured, environment. And you have your sensors inside the cylinders, and you have 5 breaking points. That's what the ASTM is recommending at various ages that go from 1 day to 28 days. Once you do these breaking points and you have, at every breaking point, the average strengths from your cylinders, and in the meantime, also the sensors, the readings from the sensors. So what we do is that we develop, the temperature. That's what we collect, and with the temperatures, we use this according to the ASTM method to do the maturity method. Or the maturity, index, basically. I'm sorry, I just got distracted. I had a phone call here, so I just turned it off. So the temperature, that's what we call, what we collect from the sensors, and we use these temperatures, with the ASTM method. We have 2 equations in the ASTM that you will use the temperature data, along with the breaking points to establish your maturity curve. The 2 methods that are currently in the ASTM, they have some constants and the ASTM provides some, average values for these constants to see, and that's what we are trying to use here in this project to see if these constants that are currently available in the ASTM are they valid for UHPC as well as the conventional concrete or not. So once we do this, we develop the, maturity curve, and that's the tool that you have before the project starts in your lab, and you provide to the folks in the construction site. Once you are in the construction site, you put your sensors in. This is an example here for, field joints or inside even conventional concrete panels. And what you do, if this is cast in place, you just put your sensors anywhere you want. You have the curve already that you have already established in the lab. And you just, after you pour your UHPC or concrete, you just start reading, the sensors, how the sensors would read, and the sensors would report the maturity. You just use your curve for this maturity. For example, did you get to the compressive strengths that you are looking for or not? That's simply the maturity method, for those who are not familiar with it. So our experimental campaign, we used, two different types of UHPC. Each one of them, we used it with 1% and 2% steel fiber just to generalize more, casts or more mixes. So we have basically 4 different, casts. From each one of them, we got 40 cylinders, 3x6, 40 cubes, 4x4, 40 cubes, 2x2, so 160 per cast, which is a total of, actually that's more than 480, 120, per cast, which gives us 480 total specimens. So that's a type here, 120 per each, or that's the total. If you look at it, from the forecast, yes. So we did 160 cylinders and 160 cubes from the different, each from the 2 different sizes. So we have a lot of data here, and the goal is to see if our data would be statistically meaningful. That's why we wanted to get as many, test data as we can, or data points as we can. We use 3 different, maturity sensors. Not to compare sensors, all the sensors are great, all of them are functioning well, all these are leaders in their in their field, but each one of them provide a different feature that's not available in the other. And we also wanted to generalize things. If we are getting temperature reading in UHPC and we just use 3 sensors, we confirm that that's what we get, then in this case, we generalize our results more. So that's the goal here. And as I always say in my presentations, we never, compare commercial products. And when we do research, we don't really care about favoring, we are not in a position to favor one product over the other, but we try to generalize our results. That's what we care about more when we do more than one product or one vendor. So that's, an example of a given cast, the cylinders, the large cubes, the small cubes. We even put sensors in larger, specimens to mimic field joints to see if the sensor would read differently inside the joint as opposed to a specimen. And these are the different types of sensors. Lumicon, for example, they have the multiple point sensor where we put it inside the joint. Geotech, they have the fully wireless sensor, and Maturix, they have a very convenient also cotton weld type of sensors that you can do. So each one of them again provides some unique features, and we wanted to benefit from all these great technologies out there. So the first thing, in terms of results, I will share with you now 3 different types of results we are looking at. First of all, the maturity curve. Do we really establish proper maturity curves when we put our sensors in UHPC cubes, or 2x2 cubes, or 4x4 cubes, or 3x6 cylinders? Which one of them would lead to a better trend and the expected maturity curve that we are looking for? So that's the 4 maturity curves we established for the 3x6, and I will talk more about how many breaking points we used to calibrate the the equations and in accordance to the ASTM. Remember that the ASTM requires only 5 breaking points. We had up to 9 breaking points, as you'll see. I will show in one of my next slides. So which breaking points would lead to the best trends and so on, I will comment in this on this in a minute. But these are the maturity curves we were able to establish using sensors in the 3x6 cylinders. The ones by 4x4, they also capture the same trend. And I think that the 4x4 cubes are even very close to each other. We can have a nice average out of this, that we can eventually present these average curves as I would say over the counter, if you will, type of maturity curves for UHPC. If you want to pick it up and use it until you develop yours, at least you have some sort of reference. But for the 2x2, we found that sensors really wouldn't lead to any consistent trends. So we are not recommending to use the 2x2 cubes for maturity curve development. So that's the first type of of results we are getting. The second has to do with the error in the maturity curve, specifically for early strengths characterization. As I mentioned, we care more about early strengths because for ABC, we want a quick answer in 12, 14 hours, 24 hours. So is our concrete there or not yet? So we wanted to see if the ASTM maturity curve would be valid for the early strengths. And in the meantime, we want to tie this to the breaking points, how many breaking points we need, and how the sensitivity of the curve is associated to the breaking points that you choose. So if we do 5 breaking points at 1 day, at 3 days, at 7 days, 14 days, and 28 days, and use this to inform the 12-hour strengths, is this going to work or not? That's what we wanted to do in this. So we had 9 breaking points from every mix that you have seen or batch that you have seen. We we tested at half day, which is 12 hours, 16 hours to 18, 20 hours and 24 hours, then 2 days, 3 days, 7 days, 14 days, and 28 days. So we had 9 breaking points, and every time we wanted to establish our curves, we either use all 9 points, which that's now beyond the ASTM recommendation. We are using more breaking points than what the ASTM would recommend, or we just use 5 in accordance to what the ASTM would require. However, if you are using 5, if you choose the 5 breaking points that at the early ages, and you establish your curves based on these 5 points, or different 5 points at later ages, or you spread your points. So we did actually up to 9 configuration. I'm just showing 2 here, but we did up to 9 configuration to see how the choose the selection of the 5 breaking points through the wide range of ages would affect the sensitivity of the results. And we start looking at the maturity curves. So here these are just 4 sample curves, right? So we did 10 configuration in total, and based on where you choose your breaking points. So here are 4 sample of them. If we use the breaking points from only the first day, which is the first 5 breaking points at 12 hours, or from 14 hours or 16 hours, 18 or 20. Now I forgot. I think it's 12, 16, 20, and 24. And then 2 days. If we use the 5 breaking points from these 5 ages and develop the maturity curve, this is what you are going to get. Maybe it's good at the beginning, but it way overshoots, and overestimates the strengths when you come towards the end. If you go with the ASTM, recommendation for 1 day, 3 days, 7, 14, and 28 days, this is the curve that you get. So it becomes, more accurate towards the end, but it over, estimates the early strengths and so on. So that's what we are trying to see here, and come up with some recommendation on how to choose our breaking points if we were to, use maturity for early strengths characterization. This is, if we zoom in the, in the early age part, and you see here now that the actual breaking points versus the curves are, all over the place. So there are some, breaking points that will lead to good errors, some would lead to, less error, and some will lead to more error, and so on. So we characterize this, and I will show this is some of the results here again. We have still the proprietary mix, 1%, 2%, and non-proprietary mix. So each of these 4 mixes, we see here the errors if we use the different configuration. So let me skip through this, and if we go beyond the ASTM and we choose even 6 points or 7 points, how the error, will look like at the different ages. And, this is the 5 points from the early strengths. So again, there is no time, so I cannot go over all these tables and details. It would take another 15 minutes to explain each of these tables, but just as to give you an idea that we looked at the error, in the estimation, in the prediction. So every time you see this error, it's the error in the prediction of the strengths when you use the developed maturity based on certain assumptions. And we are assessing these assumptions to come up with a set of good recommendations at the end of the day. So that's one thing we looked at, the errors and the sensitivity to the breaking points. And then the third thing we looked at is the convergence factors. If we were to use 4x4 or 2x2 cubes on the site, as opposed to 3x6 cylinders, so that we eliminate the need to grind and prepare the cylinders, especially if the equipment will not be available in a remote site, 3-4 hours away from any lab, would cubes work or not? So we wanted to see if there is any consistent convergence factors at both the early age and the later age between the cubes and the cylinders. And the surprise is, we found the results all over the place. Statistically, so each of these points, we had 160 cylinders, if you remember from my earlier slide, 160 cylinders between these 4 batches that were tested at, different ages, and 160 cubes 2 by 2, 160 cubes, 4 by 4. So, and each breaking point was at least 3 specimens. In some cases, we did even 4. So every point you see here is the average of 3 cylinders compared to the average of 3 cubes at the same age. And you can see here that the averages, we have 40 points now when it comes to the averages, and the averages are all over the place. We couldn't really capture a robust trend for the convergence factor for the 4 by 4 or the 2 by 2. And this is, when we zoom in, again, just this is throughout the 28-day range. And here, if we zoom in just in the first, 3 days, if we want to provide some convergence factors, at least for the early characterization for quality control purposes, we still don't feel confident that we can provide reliable factors. So we are planning to do more mixes, and we will revisit this when we have more statistical data. But the preliminary conclusion is that maybe what we thought could be a good way of quality control on the site, which is using small cubes, specifically the 2 by 2, it might not be a good method. And that's exactly why we need to do research. Is if you have a question, is it a valid question or no? So we are testing this method to see if it would work or not. So to wrap up, some of the conclusions from our work so far: the maturity trends, the 3 by 6 and 4 by 4 show very good trend lines, and that's what we recommend to be used for the maturity curve development. And users should refrain from using the 2 by 2 cubes for maturity. So that's the conclusion associated with this part. To reduce the error, we have some recommendations now, and hopefully this will be our first paper from this project. We'll try to provide solid recommendation for how to use the ASTM method for UHPC. So the points that we use to develop the curve should not be picked randomly. We shouldn't just let's say, okay, I want an early strength curve, then let me use 5 points from the early strengths, because this will lead to errors in a later age. So you cannot just pick the breaking points haphazardly. The number of points does not matter really. 5 versus 7, maybe more points is better, of course, but it's not about 5 or 7. It's more about where are you choosing these points among the range of the ages. You can choose 5 points in the right ages and get a better curve than 10 points that you choose them all in the one day, for example, or in the first 24 hours. So it's not only the number of points, but also how you pick your points. And to develop an early, age maturity, in case of curves, if the curve is not available, and we want to do something very quickly in the site, and this is, let's say we on the fly, and we have a lot of construction, problems that need immediate answers, right? So if you wanted to do a modification to your UHPC joint in the in the last minute, and you decided to increase the water amount for flowability, or you need to change the mix, so your maturity curve that you have developed in the lab is not valid anymore, and you want something really quick in the next 2 days, you don't have 28 days to do a new curve. Maybe in this case you can just use 5 points in the beginning, but that you are using this maturity curve only to assess the first, again, 1 or 2 day age strength. So this is, we proved that this might work if you use it only for the 5 5 breaking points only in the early age. And to develop less maturity curves, the ASTM distribution seems to be fine. If you look at the entire age from 1 day to 28 days, the ASTM distribution seems to be fine. But what we are recommending, what we think would be even better, and instead of using 5 points, use 6 points. And these are our final recommendation in terms of picking these 6 points, half day, 1 day, 2 days, 7 days, 14 and 18 days. We think that if you choose these 6 points, you are likely to get the most representative maturity curve for both early age and late age strengths. The convergence factor, we cannot, develop or recommend a convergence factor yet between cubes and cylinders, and this might be revisited if we have more statistically meaningful results. But for now, we don't recommend, a specific convergence factor. And what we are doing, the ASTM, I said that we are using constants from the ASTM, the Q and T. These are the 2 constants that I meant. We use these as default values according to the ASTM, but we are going to do a specific study now. That's the remaining work, to vary this T node and Q, and see if we vary these values from what the ASTM recommends as default values. Are we going to get better error, better curves and less errors or not? And we will do even experimental work. The ASTM provides an experimental method to develop your own T node and Q, which we will do for specifically and exclusively for UHPC. Then we can recommend some values as well. So this concludes my presentation, and I will be happy to have questions if we have time for questions.
Thank you, Dr. Mustafa. No, There is one question that I think you, in your last slide, you answered. So why is that we cannot use the conversion factors for normal concrete?
The conversion factors from normal concrete, so like they are not like necessarily valid. So even some of the work that was done in the Federal Highway, when they looked at cubes versus cylinders, they had slightly different convergence factors from what we use for conventional concrete. And now that these factors that we look at the data, the scattered plot that I showed, like in my slide, even this conversion factor, like which is, let's say 1, according to Beng-Rebiel, for one of the sizes of the cubes, for example, this one is not, like the range goes from 0.8 to 1.4. So we cannot even like say that this one is reliable anymore. So again, I don't want to make a solid conclusion yet. We did a lot of like tests, as you have seen. These are like more than 500 points or 480 points, but still we will do more points and see if we can revisit this recommendation.
Okay, thank you.